Okay, good morning. Um, Come to this lesson, which is the first in chapter one, that is basic probability. Okay? Basic probability. And the first concept that we want to deal with is a random variable. To understand what we mean when we talk about a random variable. Okay? So we are saying an experiment whose result, okay, an experiment whose result cannot be predicted, cannot be predicted until it is observed, um, is called a random variable, or maybe random experiment rather. Okay, random experiment. Okay, so that is random. What we mean by a random experiment is an experiment whose result we are not sure of, not until it is observed, not until it is noticed, not until an experiment has been conducted. That kind of an experiment is a random experiment. Again, by random experiment, we mean that anything is likely to occur. Okay, we are not sure. Anything is likely to happen. Okay? So when you conduct an experiment and you are not sure what is likely to come out, you can't predict. It means that experiment that you are doing is just random. An example, give an example of when we throw a dice. Okay? When we throw a dice, okay? When we throw a dice randomly, okay? Randomly, okay? The result that throw is uncertain. Is uncertain. We are not sure. Anything is like happen. If you throw a dice, any of the six numbers may just pop up. We don't know. Okay, we're not sure. In other words, we can get any result, get any output, okay, between 1 to 6, okay? So when you throw a dice, you cannot tell what will show up as that dice runs, but any of the numbers from 1 to 6 just show up. Hence, because we are not sure, hence the experiment is random. Because any of these numbers is it likely to appear Okay, sorry, I muted myself with some noise. Okay, so that's what we mean by a random experiment without sure of anything like to happen. That is a random experiment. Okay. Now, if we look at the example one, they are saying if a coin is tossed. Okay. Outcome of the experiment or the outcome of that toss of experiment uh, is that it will either come up as tail denoted by T or 0 or as head denoted by H or 1. When you toss a coin, either be a head or a tail. Okay, head is denoted by H or 1, tail is denoted by T or 0. Any of these can happen, isn't it? All right, we're not sure. That is a random experiment. That is a random experiment. Okay, this also implies that the result. This also implies that the result will have any of the following. Okay, the result will have one of the following or elements of the set HT, or because we said H is 1, so to be 1. So the result will either be head or tail, 1 or 0. Okay, that's what we mean. So once a coin is tossed, either head, tail, or up. Head is denoted by 1, tail is denoted by 0. So either 1 or 0 or up. Okay. Example 1.2. If a die is tossed, the result, because we are talking about a six-sided dice, result of the experiment, which is random, is that it will come up with one of the numbers in the set 1, 2, 3, 4, 5, 6, right? So once a dice is tossed, any of these numbers may pop up. Okay, in all this, our experiment is random. Okay. If you look at example 1.3, all right. If a coin is tossed twice, okay, there are four outcomes. Possible outcomes. Okay, that is, if you toss a coin for the first time, the head appear, okay, and as you toss for the second time, head may appear as well. You have got head. Okay, that is the first possibility. Then it is possible that you toss for the first time, head appears, but for the second time, it is the tail. Or as you toss for the first time, you have tail. Then for the second time, you have got the head. Or indeed, first time it is tail, and the second time it is the tail. So there are these four out. All right. Another example, example 1.4. Okay. Let's suppose a machine makes both. Okay. Let's assume that a machine makes boats. Now, the result of the experiment is that some may be defective. Okay, so we are saying this machine makes boats, but the result could be that some boats be defective, while others may just be okay. Okay, defective. While others may be non-defective. This is what we have. Okay, this is what we expect. As this machine is making these boats, there's a possibility that some boats may be defective. Okay, and some boats or other boats would just be fine, they would not be defective. Implying that in terms of a set, we have a state where we have got defective ones, boats, and non-defective. And this represents the sample space. Non-defective boats. Okay. This will represent all the boats that will be both effective and non-effective. These are the possibilities that we expect. And because we are not, each time the machine is producing these boats, whether it will be fake ads or not, the experiment is random. So that machine is producing random boats. Anything happen. Okay, okay, we've got another example. Example 1.5. Example 1.5. Let's suppose that, I'm getting all these examples from the book. Let's suppose that an experiment, okay, an experiment consists of measuring lifetime, okay, lifetime of an electric light bulb. Or we say bulb, okay, produced by a company. Okay, let's suppose that an experiment consists of measuring the lifetime of an electric light bulb, um, an electric light bulb produced by a particular company, any company. Okay, now what could be the results? So the results of such an experiment is maybe a time, and let's assign time as t, and in hours, that maybe lies in some intervals, all right? That is maybe 0 should be less or equal to time, and the time is less or equal to 4,000. Okay, where we assume that where we assume that some writes thus more than 4,000 hours. Okay, so what we are saying is when this experiment is conducted, we are trying to measure the lifetime of each electric light bulb that is produced by a company. Now we are saying the lifetime, they lie within an interval, let's say 0 to 4,000 hours. Okay, so meaning that once a bulb is produced, it is expected to be in this interval, right? It's expected to be in this interval, all right? But that may not always be the case, not always be the case, okay? So as we produce, we may find that we get a bulb with a lifespan of 0 to 4,000 hours, but some may even be more than that. So we can have 0 to 4,000 hours as desired, but some may be more than that was an experiment that is being done randomly. Okay, so this machine may make bulbs whose lifespan is this range, but as well, they have some where the lifespan more than that. Okay. Okay. Then the next the concept that we must understand, like I mentioned earlier on, is the sample space. So if you look at an example that we had, where we talked about you tossing a coin twice, and we said we have got possible outcomes, four possibilities. Now head, tail, tail, head. When you consider all these four possible outcomes, these represent what we are calling a sample. That is sample space. Okay. And now let's put up a standard definition. Let's put up a standard definition. Okay. So you're saying a sample is the set of all possible outcomes. That is a sample space or result. A set containing all the outcomes, the sample space is the universal setting. Okay? And we must emphasize that it's of a random experiment. A random experiment, right? Now, let's look at some examples which we have already. Suppose a dice is thrown, okay, and must be thrown randomly, okay. Then, what is our sample? Sample space noted by S is equal to 1, 3, 5, 6, containing all these possibilities. Okay. And you can see clearly that this sample space contains some odd and even numbers. All right. Example 7, 1.7. If we toss a coin twice, like we said, and use 4 to represent tails, that is 0 rather, and 1 to represent heads, okay? Then the sample space. Sample space, like we've already said, is S equal to H T T T H, right? Now, typically, if we use 0 and 1, so this is 1, 1, 1, 0, 0, 0, and 0, right? Now, graphically, we can represent this as, okay? We can represent the sample space S on the Cartesian plane. Cartesian plane as follows. So if you have got the Cartesian plane like this, you may have 0, you have 1 here, and you have 1 here. So the first one is here, 0, we can present 0, 0. Or if you want to start with 1, 1, 1, 1 will match here. So you have the point here, which is 1, 1. Then this is followed by 1, 0. X is 1. Here is 1, 0. And the other one is 0, 0, 1. Okay, this is what you have. What we have. And that's what we mean by a sample space. Now, from here, we can pick up some remarks. Number one, that a sample space has finite number of points. Then it is called a finite sample. For example, we have just from an example where you post a point. How do you expect? Expect head, tail, head, right? Or and 1, our sample space would be 1, 1, then 1, 0, 0, 0, and 1, 0. Now, because we have finite points, we have a finite number. Like in this case, when you count 1, 2, 3, 4 elements, it means this sample space is called a finite sample space. Okay, called a finite sample space. Okay. Then number 2, what is the point that we must remember? If the sample has as many as there are natural numbers, right? E.g., maybe we say 1, 2, 3, up to infinite. Okay? In other words, you have got infinite points, this sample space. Then the sample space is called countably infinite sample. That's what we mean. If you have a sample space where you have infinite points, okay? You have infinite, and these points are discrete. Then that sample space is referred to as countably infinite sample space. Okay? Now, what is the third point? If a sample space has as many points as there are in some interval, okay? On x-axis, e.g., 0 is less or equal to x, and this is less or equal to 1. Such a sample space is called, non-countably infinite sample space. Non-countably infinite sample. So, in short, we are saying if a sample space takes an interval, okay? If a sample space takes an interval like this one, then that sample space is called the non-countably infinite sample space because it takes so many values, all right? Because from 0 to 1, there are so many values, okay? You can have 1, 0.002, 0.1, takes many values, okay? So that is called non-countably infinite sample space on an interval. So there are so many values. Okay, what could be the fourth one? A sample space. A sample space, which is finite, or countably infinite, is called a discrete sample if a sample space is finite, so if a sample space is finite, okay, or countably infinite, that sample space is called sample. This takes us to the first two examples. So here we defined a finite sample space, okay? To have finite number of points. A finite sample space like this, where I've got the head, tail, head, tail, okay? And also countably infinite sample space is called a discrete sample space. In other words, a sample space that is not on an interval, a sample space that is not on an interval is a discrete sample space. Okay, so this one is not a sample space because it's on an interval. Okay, so the fifth one is the sample space which is non-countably infinite, is called a non-discrete sample space. What does it mean? Simply means, the example that we had in part 3, where we are taking an interval. That one is referred to as a non-discrete sample space. In other words, a continuous sample space. Okay? It is a continuous sample space because it takes multiple values. Okay, here are some of the points that we need to appreciate. Okay, next, we need to define what an event is. Okay, now by definition, an event is actually a subset of a sample space. An event is a subset of a sample space. Sample space. Okay. What do you mean? That is a set of positive or we may just leave it open and as a set of all possible outcomes. Okay, we'll come to the restrictions for probability later on. So if you have a sample space, if we have a sample space, e.g., if we have a sample space, e.g., 1, 2, 3, 4, 5, 6, okay, then if we isolate the numbers in there, for example, 1, just 1 is an event in this regard, right? Is an event. We are saying an event is a subset of sample space S. And sample space S is a set of all possible outcomes. Okay. Now, if the outcome of an experiment is an element of A, then we say an event A has occurred. So what we are saying is that if you conduct an experiment and that the outcome, okay, is an element A, then you will say A has happened, right? A has taken place, okay? Now, note therefore that an event consisting of a single point, a single point of S, like the way the example that I gave, say from the sample space of 1 to 6, we single out only one as an event. Okay, so an event consisting of a single point. Okay, of the sample space. Okay, single point of the sample space, which is S. What do we say? Then that event is called a single one, simple rather, or elementary event. We are saying an event consisting of a single point of S. Okay? An event consisting of a single point of S, let's say 1, that is one from the possible outcomes, that is 1 to 6. We pick out 1. All right? That event is called a simple one, a simple event or elementary event. So if you have a sample space, then we have an event consisting of only 1 point, then that event is called a simple event because it only has 1 or 1 point. Simple or elementary elements. I hope that is fine. We can look at an example, which is example 1.8, that book. Suppose that we toss a coin twice, okay? The event that only the head stands up, only the head stands up, only the head comes up is, so we're saying, suppose that toss a coin twice, and that only head comes up is 1, 0, or 0, comma 1. And this is a subset, which is a subset of S, the sample space. In this case, the sample space has 1, 1, 1, 0, 0, 1, and 0, 0, 0, 0. Now, what do we mean by 1, 0? Remember we said let head represent 1 and tail represent. So if we're interested that only come up, it means the first toss, we have head, only head. Okay, we have got head, tail. We should have one head, meaning that we cannot have head and head. So we have got 1, 0. That is head, tail, or the converse. Tail, head. Now, when you look at 1, 0 and 0, 1, these are sample space. 1, 1, 1, 0, 0, 1, and 0, 0. This is a subset. It is an event. Okay. Okay, so if we were to represent it again on the Cartesian plane, okay, so on the Cartesian plane, we have the following. Here we had 0, 0. Here we had 1, 0. Then here we have, somewhere here we have 1, 1. Here we have 0, 1. And now our interest is 1, 0. So we have got this. What we have, and you check this, what is what we have. And this is just part of these four. Okay. Okay. We can also put up some other remarks here. Max. Number 1. Sure or certain events. What do you mean by sure or certain events? These are events that must occur. Okay. These are events that must occur. It's a must. Okay. Then these are events that must occur. Must occur. Okay. These are sure events and events. Okay. Next one is impossible event. What do you mean by impossible events? Events which cannot occur. Okay. This can be in terms of technology, definition, so on and so forth. Okay. Now, we talk about operations on sets. Operations on sets. The first one is number one, the union of two sets. To define these sets, or to define the union of two sets, I'll pick two sets as well. Let's say set A and set B. So by definition, we are saying let A and B be two sets. Okay, be two sets. Then the union of A and B is the set. It is the set that contains or that consists of all the elements, all the elements belonging to either set A or set B or both. That is the union of a set. We are talking about a set of elements that consists or contains all. The keyword is all the elements belonging to either A or B. So the word means union in this case. All right? Either A or B or both. All right? The collection of all the elements in set A as well as set E is referred to as the union of set A and B. It implies that symbol is the event. So now we are combining sets with probability. Is the event, okay, either A or B or both. Or both. So union is represented by this letter O in this regard. Word rather. We have that. Or A or B. What does it mean? We have A or B. We're talking about the union of these. Okay? The union of these two, including their intersection. As long as elements are not repeated. Okay? Number two, intersection of two sets as well. So define that we need two sets. So saying by definition, let A and B be two sets. Okay? Then what are we saying? Then the intersection section set of set A and set B denoted by A intersection B, okay, is the set composed composed of four elements. Four elements which belong to both A and B. So the key word here is both implies intersection as well as and. It implies that A intersection is the event that both A and B. So both implied intersection. Okay, both implies intersection. The next one is complement of a set. Of a set. So what do you mean by a complement? A complement of a set is not defined in isolation. There must exist another set. In this case, we are talking about the sample space. If a set A is a subset of a sample space, okay, then a complement means the elements not contained in A but are within the sample space. Okay. So a complement means all the elements in the sample space, excluding those in say A, as simple as that. So by definition, we are saying let A be a subset of E. Then E is the universal set. Once we can use X. Then the complement of A, that is A the power C or A dash. The set of all those elements in E, but not in A. That's what we mean. That is a complement. So what does it mean? A complement is the same as E minus A, or you can say A complement is the same as the sample space minus A. Okay? This implies that A complement, the event that not A. That's what we mean. Example. So these examples where I'm not indicating numbers, it means I've just generated them. Examples with numbers are exactly what is in the book. So suppose that our sample space is 1, 2, 3, 4, 5. All right. And A is 1, 3, 5. List A complete. Okay. So we are saying A complement means sample space minus A, right? So this simply means from our sample space, we get rid of what? Of 1, 3, 5. What do we have? 2, 4, 6. This is a complement. Therefore, a complement is just the same as even numbers in that set. Okay? Set of even numbers. Okay. Then we move to difference of set. Difference of sets. Difference of sets. To do that, we need two sets. So by definition, we would say let A and B be two non-empty. Okay. Then the difference of A and B denoted by or denoted as A minus B or A slash B is the set of all of values or indeed elements of A which are not members B. Okay, so this implies that A minus B is the same as A intersection B complement. Okay. Example. Suppose that A has these numbers 1, 2, 3, 4, 5. Six and B has 2, 5, 6. Then A minus B is equal to, in this A, we remove the elements that are in here. So 5, A minus B as the 1, 3, and D, that is A minus B. Okay. Then we have disjoint sets. Disjoint sets. If A and B are two sets such that A intersection B is phi. Phi means an empty set. Then A and B are disjoint sets. Okay, then you present this in a diagram. We have got this. We have got A, B, 1, 2, 3, 4, 5. The sample space. Sample space, in this case, A and B are joint sets. Okay, so that's what we mean by joint, where the elements have nothing common. Those elements are referred to as the joint. In other words, intersection set of these is the empty. Sets are said to be disjoint. I hope that is fine. Okay, these are some of the terms that we must master. Okay? These are some of the terms that we must master. So for this lesson, I think what we've covered is sufficient. And end here. If there are questions, you can let me know so that when we have a live class, ask them. Any clarifications, please let me know. I should be able to address them on WhatsApp. Okay, see you next time. Bye bye.